Hello, this is a video about COMP345, Advanced Program Design with C++. This is for week 5. This is slide set number 5, video 1 of 2. So today we're going to be talking about, well, the slide set 5 is about arrays and how the different ways you can actually do arrays in C++ or use arrays in C++. Today it's going to be about statically allocated arrays. If we go straight to the slides, share here. Sorry. Okay. Okay. So there are essentially 3 ways that we're going to see how to do arrays of objects is either statically allocated arrays or dynamically allocated arrays, or using some libraries, including the STL containers. So what is an array? So we're just basically going to go into the general concepts, which you probably already know, but just to make sure we're on the same page. So what is an array? An array is a collection of data elements, which are all of the same type. So when you define a class, for example, it is a collection of data elements, but which are potentially of different types. So as they are all of the same type, then they don't need to have a name. So you can actually refer to them using an index, which is much of what we're going to be discussing today, because when the compiler is actually translating the access to your arrays, it would be using offsets out of the index number that you are giving. So this is essentially a very simple kind of aggregate type, and you can create arrays of elements of any type. So you can create an array of int, or if you create your own classes, or if you have access to libraries which define other classes, then you can define an array of any type, which would contain elements of all of the same type. So arrays can be either statically allocated, which means that it's a variable that you declare, for example, in the body of a function. Then the entire array in this case is residing on the stack frame of the function in which this array is being declared. You can also have dynamically allocated arrays, which we'll talk in the second part of this slide set in the second video. So in this case, you can actually change the size, because one of the things I didn't say is that the statically allocated arrays, their size is fixed for the entire duration of the program, or might I say, the entire duration of the execution of the function in which they are declared. However, if you declare a dynamically allocated array because you're using pointers, then you can actually somehow, as we will see later, change the size of the array, or change the array to which the pointer is pointing to, which this array might be in time of different sizes. So yes, it's called dynamic array, but it's not very dynamic. If you want to have something that's very dynamic, you would have to use something like STL containers, which include a mechanism to actually dynamically change, adapt to the size that you are currently using. So you have to expect when you're using any kind of array in C++ that the size it's not easy. It's either impossible for a statically allocated array, or not so easy to actually change the size of an array as you're executing your program. If you want to have flexibility, you should use STL containers, or there are some other libraries that provide arrays that can change in size. So how do you declare an array? Well, that's same thing, exactly the same syntax as you have in many programming languages, including Java. So you can declare, for example, an array of 5 integers named score. And then basically what happens if you have, of course, 5 different integers that are stored in this array. In C++, when you declare an array like this, then they are stored in the computer's memory in a contiguous memory space, which is a central aspect of what is a statically allocated array. So that's why it allows you to refer to them using an index. So for example, here, the first element would be score of 0, and then the last element will be score of 4. So it's important to realize that the index starts at 0. As we will see later, it has to do with how the offsets are being calculated. So the fact that it's declared as size 5, and then that the last index is 5 minus 1, which is 4, is of course creating potential for bugs as you, for example, loop over all the elements, which is particularly important in C++ because, as we will see later, the there's no such thing as checking for an index out of range when in a C++ program. So you can actually access elements of the array outside of the range, as we will see later. So that's even more problematic if you go out of range. So how do you access the members? So essentially you use the index or subscript of the array. So note that here you're using the square brackets. So it's important to realize that here also you use square brackets, but these square brackets here don't have exactly the same meaning, whereas here you're specifying what's the size of the array score, whereas here you're specifying an index of a specific element inside of the array score. Okay, so yes, it's both of square brackets, but they don't have the same meaning, so they don't have the same rules in particular. Well, in particular is that when you define the size here of the array here, for example, 5, the value that you put here must be a constant. So here it's a literal integer 5, so it is a constant. You could also use variables, but these variables would have all to be constants. You could have an entire expression, but then all the constituents of this expression would all have to be constant, which we call a constant expression. So whatever you define the size as, the value of the size must be, the compiler must be able to determine what's the value of the size at compile time using only constant values. Okay. So why is it so? Because when the compiler determines the size of the array, the compiler will make it so that a block of memory of a fixed size is going to be reserved on the stack when you execute the function in which this array is being used. So this size will not change, and this size needs to be allocated at compile time, or determined at compile time. So that's why the compiler needs to know what is the size and needs to be a constant. However, of course, when you use a subscript, you can use any integer value inside there, including an expression, which is, of course, not constant. So here's a simple program. So essentially here you declare an array of 5 scores, 5 ints named score. And then here, of course, very frequently you would use a for loop to actually loop over all the elements. So very simple here. And then you have another for loop that loops over all the elements here. Okay. So very frequently, you would actually have this same construct here. You declare an array and you loop over the elements of the array, either to fill the elements in the array or to access them or process them. Very common is what you do. A very common thing you do with an array. So what is the range? So the range starts with 0 and then ends with size -1. So the very important, as we will see later, is that to understand that the compiler will actually use this value of the index that you provide, and will use it to actually determine an offset versus the beginning of the address, beginning the storage of the array, in order to move down the array in order to access an element of specific index in the array. Okay, so it's using basically the compiler is computing an offset value to determine where in the computer's memory you want to access, which element in the computer's memory you want to access in the array. So very important, as I mentioned earlier, it's extremely important that you realize that, especially if you come from a Java background or other similar languages, which will actually check at runtime if you're going out of range when you access elements of the array. C++ will not make such a check. Okay, so you can actually go out of range. We will see in the next slide what might this mean, or what this might mean. So the compiler will not check if you're going out of range, no, because in most cases it can't. And then even the runtime system will not make such a check. Okay. Why is it that it doesn't make this check? Because of course, making it every time you access, if everything time you're accessing an element of an array, which might be extremely frequent, if every time then you check if you're in the range, then that basically is using some computational cycles. Again, C++ was made for efficiency, so it does not make these checks to save time. So that's why very often if you go out of range, your program might continue working and then you don't realize it and it's actually doing something wrong. So it's up to you as a programmer to stay inside of the range. So of course, this is leading to a lot of different bugs, possibly, and also, some people, malicious programmers, let's call them like this, frequently use this feature as to be able to, for example, scan the memory of a certain process and basically change things inside of the execution of a process by injecting some malicious code in a program, for example. Okay, so one thing that you can do, the point is that when you define a static array, the size is determined at a compile time. So after you compile this program, there's no way that this program will ever be able to, the execution of this compiled program will ever be able to change the size of the array. Now, what if you would want to be able to change the size of the array and then recompile and then run the program with a different size of array? Now, of course, you can do that. So, but then, the program is likely to actually refer to the size of the array in many different places in the code. So what you want to do in these cases, if you want to have this flexibility across different compiled versions of your program, then you could define some constants, and then you use this constant to define, for example, the size and a number of elements in the array. So that would actually improve on the readability of your code, improve the versatility of your code, and of course the maintainability of your code. If you want this array to be able to change the size of an array across different compiled versions of your program. So after you would have defined the size, that constant that defines the size of the array, then you use this constant to determine the size of the array itself, as well as the marker to actually stop your for loops that are manipulating or looping over elements of this array. So that makes it so, for example, if you have code like this, and every time you refer to the size of the array, you refer to this constant variable that you have defined. Then if you want to change the size and recompile and execute the program with a larger or a smaller size of array, then the only thing you have to do is to change this here. If you wouldn't have that, then you would have 5 here, and then you would have 5 here too, and so on. So anytime you would refer in your program to the size of the array, you would have to make a change, which is of course very error prone. So if you declare a static array in a program and you want to have the possibility later on to change the size of the array and recompile, you should have to use that. Okay, so how is it stored in the computer's memory? So the most important thing is that when you declare a static array, then it's actually stored in a contiguous memory space or block of memory. So another thing that's important to understand also, as I will explain in more details later at the end of this video, toward the end of this video, is that you can actually refer to the elements of the array using a pointer and pointer arithmetic. So for example, if you have in a program here in a function, a variable named x, and then which is an int, and then an array of 4 int named a, and then an int b defined in sequence like this, then when you execute the program, then it's going to be stored like so here. Now here I'm assuming in this particular example that, for example, an int would be stored into 2 consecutive memory cells. So that so that x here is stored in these 2 memory cells, a of 0 is stored here, a of 1 is stored here, a of 2 is here, a of 3 is here, and then b is here. Okay. So the thing is that as you are manipulating a, you can actually use pointer arithmetic. So that would be using the notion of that the array would what is called decay into a pointer. So it's basically meaning if you're declaring an array, for example, a, if you go a plus 1, then inherently what the compiler will understand is that you want to increase the value of the pointer to the first element of A. Okay, so in this case, A was of type array of 4, whereas if you go A plus 1, then meaning is the value of the pointer, the value of the address that points to, that is the address of the first element of the array A plus 1 element in this array. Okay, that's what is called, I will explain later, that's called array decay to a pointer. Okay, so central aspect of actually using arrays and understand how they are part of computation. So the idea which comes hand in hand with this is that as the compiler is actually figuring out how to access the members or the elements of an array, it will actually compute offsets with reference to the first memory cell address that is containing this array inside of the memory. So it knows what is the address of the first memory cell. Then depending on what element you want to access, it's going to compute an offset with regards to this first, the address of this first memory cell, and then we'll move and then be able to access other elements in the array. This notion of offset is very central to computation of static arrays in C++. Well, that's how it is done in all other programming languages, but in C++ it's much more apparent, and you can actually use it much more explicitly in your program. Okay, so another thing is that as C++ will not check whether you go out of bounds. For example, let's say you have this variable x here, and then the array of 4, and then b here. So if you refer to a of 0, then actually that refers to the int that's stored here. If you refer to a of 3, that refers to the int that is stored here. So you see that is the offset that is being calculated by the compiler in order to figure out what is the address of each of the elements. So you see that it's actually for a of, let's say, 2, it's going to compute the offset a, which is the address of this memory cell here, plus 2 times the size of an int, which is the size of the type of the elements, which is going to be the address of this plus 2 times the size of an int, which is going to be here. So then it's going to access this if you want to access a of 2. However, because of this, way of computation, you can actually put, for example, A of 4. You can refer to A of 4. Well, A of 4 would be the address of the first element of A, the first memory cell that contains the first element of A, plus 4 times the size of an int, which is this address here. So if you actually, in this particular program, if you access A of 4, that's going to actually be making you access the value of B. Okay. So of course, then if you, for example, put a value inside B, inside A of 4, you actually change the value of B in this particular case. So you see that it's creating potentially a lot of different kinds of problems. And the same, even the same if you go A of -1, so that's the address of this here, minus 1 times the size of an int, which is actually making it point here. So if you change the value of A -1, you're changing the value of X. Okay, so how could you initialize the values of an array as you declare it? For example, when you want to initialize an int, you would go equal to 0. Or using the squiggly brackets notation. If you want to initialize an array of one dimension, then you would use still the squiggly brackets here and combine with the equal. And then this would actually put 2 in A of 0, 12 into A of 1, and 1 into A of 2. Okay. Particularities is if the number of values that you put here is greater than this number here, then that would be flagged as a compiler error, compile time error. If you put some or less, let's say you would be going int children of 3 is equal to 2, then I would be initializing the first one to 2 and all of the other ones to 0. If the size, you could actually not specify the size here if you provide an initialization list like this here, in which case the size would be the number of elements that you have put in the list. So you can determine the size of an array as stored in the computer's memory using the size of function. So for example, if you, in a particular compiler, if you declare an array of 3 integers, then it might say this is 12 bytes because of course, then one integer would be 3 bytes, 4 bytes. And then you can also declare an array of 2 by 2, in which case it's going to be 16 bytes. And you could have an array of 3 double, which would be 24 bytes. Okay. That depends, the number of bytes that is used to store an int or a double depends on which compiler you are executing on. So you might run this exact same code in 2 different compilers on 2 different compilers, and then it would give a different value. So you can also pass arrays pass arrays as parameters to functions, but there is great limitations to that. So it's possible, but it is limited. So if you when you pass an array as a parameter, then you remember when I said that the compiler will actually compute the offsets. Calculating the offsets, especially for 2-dimensional arrays, actually requires what is the dimensions of the actual array, as we will see later. So that's actually what brings the limitation. So in order for the compiler to determine what are the offsets, let's say you pass an array to a function, then the compiler needs to generate the code of this function. So how will it know what are the size of each of the offsets of each element, especially if it's multidimensional array. So it needs to know what is the address of the array or the starting address where this array is stored. It needs to know what is the type or the base type of this array. If it's an array of int, it determines what number of bytes you need to skip in order to access each element or the offset. And then it needs also to potentially know what is the size of every dimension of the array. For a one-dimensional array, the only offset that needs to know is what is the size of an element, which is written actually in the array declaration or parameter declaration. So if you want to pass an array to as a parameter to a function, then this is the syntax you would have to use. So you don't have to specify here what's the size of this array. Because the compiler does not need to know what is the actual size of the array in order to compute the offsets. Okay. But very important to understand that as you hear, it appears that you are passing this array by value, hence that this array will be copied as the array is being passed, as is what's customary for pass by value. But there's no such thing. If you pass an array to a function in C or C++, what you're in fact doing is passing a pointer to this function. Okay. So no such thing as even, it's not the same meaning as pass by value when you pass an array by value. Passing an array by value is in fact passing a pointer. So you would actually, you would literally declare an array of int and then pass it onto the function. And the function would actually do an operation which is called decay on this array, which would actually somehow transform this array into a pointer and then pass this pointer to the function. Okay. I will come back at the end of this lecture or this video about what is decaying an array to a pointer. So in fact, what's happening, because you pass a pointer, what's happening is that the array is not copied. So in fact, if this function that you're calling is changing the values inside of the array, it is actually changing the values inside of the original array that was passed by the calling function. Okay. Another thing is that my func, this one here, as you see, is not aware of what is the size of this array. Okay. So, so it needs to be passed as another parameter in order for you to be able to, for example, if you want to do a loop that loops over all the elements, the array itself, the function does not know what's the size of this array. So it needs to be passed as a second parameter. So you see that there's limitations to using static arrays when you want to pass them to functions. There's plenty of examples on this in the lab exercises. So how do you return an array? So you see the reason why arrays cannot be passed as parameters is that if you pass an array by value, then you would have to make a copy of the array. That's not so bad if you're passing an array of 5 int, but what if you're passing an array of 1,000 by 1,000 by 1,000, basically a million or a billion elements are being passed, an array of a billion ints is passed to a function, then a copy would be made of this entire array when you're calling this function. Extremely memory inefficient. Okay, so that's why in C and then later on C++, there's no such thing as passing an array by value and making a copy of an array as you pass it by value. Pointer is passed, which is very efficient, but brings its limitations, as I just explained. So the reason for that is efficiency. Okay, the same thing goes when you want to return an array in C++. You're not allowed to return an array by value. Okay, you must return a pointer to this array. So this was for introduction to statically allocated arrays, specifically one-dimensional arrays. Now, what if you want to have multidimensional arrays? So it's not an entirely different concept, except that the mechanics of how the offsets are calculated needs to be explained better or in more detail. So this is how you would declare, for example, a two-dimensional array of characters named page of dimensions 30 by 100. So that allows you to have all of these different elements that you can refer to in this array of characters. Pretty standard. Again, this is the same thing as what you would have in many, many different programming languages. Let me just move that here. So important to realize, even if it's multidimensional, it is still a static array. A multidimensional static array is stored in a contiguous memory block. Okay, so if you would have a two-dimensional array of 3 by 4, then essentially what you would have is the first row, second row, and then third row. And each of the rows is composed of 4 integers. Okay, so that's how it would actually be stored in this particular order, that it would actually be stored in the computer's memory. And the mechanics of the offsets is the same idea. Okay, so for example, if you use A and you compute an offset from it, then the first element is stored here, second element is here, and then, but the point is that the element after the last element of the first row is the first element of the next row, and so on and so forth. And if you go to three-dimensional, then you would have every row is stored here sequentially, and then here, for example, here you have the first plane of this cube, and then you have the second plane of this cube. Okay, that's the first plane in the cube, and that's the second plane in the cube. Okay, so you basically loop over all the elements of a row, and then you loop over all the rows of a plane, and then you loop over all the planes in a cube, and so on and so forth when you have more and more dimensions. Okay. So how do you pass a multidimensional array as a parameter? So as we saw in the one-dimensional case, in the one-dimensional case, you didn't have to specify what's the size because the offset can be calculated using the type itself. However, if as the compiler generates the code for this here, it needs to know what are the offsets. Now, what is the offsets here is determined by how many elements there are, for example, in a two-dimensional array, how many elements there are in each row, which is this number here. So if you want to access the second row, then you need to skip 4, which is this number here. So that's why you need to pass to specify inside of the function declaration or the header of the function for this particular parameter, you need to pass what is the size of every dimension after the first one, so that the compiler can figure out how to compute the offsets to access the elements of this array. So you see that this actually binds this function to be a function that receives an array of any number of elements by 100 elements. Okay, so that greatly limits the reusability of this function. This function is bound to computing a very specific kind of array. That greatly limits the usefulness of static arrays, especially multidimensional. Another thing also is that if you want to compute, for example, you want to loop over all the elements of this two-dimensional array, and you absolutely need to know what's the size of the first dimension here in order to do your double for loop here. Okay, so here we go a little deeper here in this example. So yes, so this array here that I'm declaring using two precompiler variables is basically an array of 3 by 4, which is initialized here with these values. And here I have a double for loop here. It's basically outputting to the console each of the values that are stored in my array. So you see that's using double indexes here, just like you would do normally, let's say, in your Java program. So nothing new here. However, what I want to show here is how you can actually access the elements using decay to a pointer. So as I mentioned earlier, this array here, the type of this array table is an array of 3 by 4 integers. However, you can actually use pointer arithmetics, or arithmetic to actually access sequentially all the values in the array. So for example, if you would go use the table, the address of the first element of table, and then you would increase this address with 1 time the size of an element or 1 time the size of an int, then you would actually now have the address of the second element. Then you increase it again with the size of an int and you access the third, and then so on. And then you would eventually access all the elements here. That's a very efficient way to loop over all the elements of an array, because it uses two things. That uses the assumption that it's stored contiguously, and it uses the assumption that you can use the addressing of all the elements of the array in order to loop over all the elements. Okay. Now here you can actually use this notation here, which I will explain in the next slide, which uses the notion of decaying the name of an array into a pointer. So essentially here it goes, the point here is that you have table and then you have +1. Now, there's no such thing as adding two arrays. So if you have two arrays, you cannot, two array A and B, you cannot, there's no such thing as a plus operation on arrays, okay, first of all. Now, what does that mean if you go table plus I? So the thing is that the compiler is going to understand here that you want to actually take the address where this table object is, the first element of this table object is stored, and increment this address by I times the size of the elements that are stored in this array. Okay, so this is how the compiler is going to basically decay, what is called decay, the name table into an address, okay, or some kind of pointer. So it basically decays an array into a pointer. And then after this table here has been decayed to a pointer, then you go +1, and that basically increases the address by 1 relative to the base address of the table. Now that actually gives you, if you go table plus I or table +1, then it actually will increase the pointer value, and then it's going to be enable you to actually point to different elements in the table. Okay. So let me go to the next slide, and then we'll come back to this one. So that's the general notion of what is called array decay into a pointer. So I'm going to explain this concept in more detail here, and then we'll come back to the example I just presented. So as we saw, for the sake of efficiency, the arrays are not passed or returned as values, because that would entail that you actually are making copies of these arrays, which can be extremely wasteful of memory and computational time. So what you do in C and C++, if you pass an array, you pass a pointer. So that involves the notion of decaying Decaying is a technical term in C++, which is used for many other things, which can become extremely technical. So here we're just going to talk about decaying of an array into a pointer. Decay is not only about decaying an array into a pointer, it's a very general concept, which again can be extremely technical. We're not going to cover the other kinds of decay in this course, okay? But you have to know, possibly you're going to have to face this issue if you're doing some particular, I would say, advanced C++ programming. It's seldom that you see the notion of decay being problematic or something you have to know as you are using C++. Okay, so here, let's say we have this three-dimensional array of an array named A of dimension 2, 3, and 4. So I have my rows of my array here, and then I have two different planes in this array. So that's plane number 0 here, and that's plane number 1 here. In each of these planes, I have, for example, the entire first row that is here, the second row of the first plane, the third row of the first plane, then the first row of the second plane, and so on and so forth. Okay, so that's how it's stored. Now this allows me to use the index notation, which is very easy to understand. It basically refers to exactly the sizes that I have here. So the size in the first dimension is from 0 to 1, and the second dimension is 0 to 2, and the third dimension is 0 to 4. So very intuitive way to refer to each of these elements. Now, it's important to understand that when the compiler is interpreting this here as it's making the translation, it will eventually come up with a formula like this in order to compute the offset of each of the elements that you may be referring to. For example, if you're referring to this one here, A111, then basically it is the address of A, which is this address here, plus you would have to skip one plane because you're referring to A of 1. And then after you have the address of the start of the first plane, which is this one here, then the second one you're referring to is this one here. So you would have to skip the first row in the second plane. And as you're referring to 1, you would have to skip one element in the second row of the second plane. Okay, so that's basically how it computes all of these offset here. So if you go A111, it's computing this here, and it comes with a number, which is the offset relative to the starting address where this array is stored. Okay, so that's what the compiler does when it actually is computing how to access these elements, given what is the indexing that you are giving. Okay, so you see here that when it wants to compute this number, it needs to know what is the size of a plane. What is the size of a plane is the size of the two last numbers here. So it needs to know what is the size of each of the last two sizes or dimensions of the three-dimensional array in order to compute that. In order to skip an entire row, it needs to know what's the size of a row. In order to skip an element, the only thing it needs to know is what's the type of the elements in the array. Okay, so you see that's why it doesn't need to know the first number. Okay, it needs to know all the numbers except the first one. Okay, so that's the how the compiler will compute the actual offsets at compile time. You could actually yourself write this as code, and it would work. Okay. Okay, so then in my example here, I was using this, some might say strange notation here, which is actually an example to show how an array can be decayed to a pointer. Okay. Okay, so let's take, for example, this, which is what I was using in my example program there, except that my example program is 2-dimensional and not 3. Now let's go to the next slide and see what's the meaning of that. Like, what's the meaning of this line here? Essentially here I'm decomposing this line or this expression into its constituent expressions. Okay. For example, it refers to A. So what is A? A is of this type. So A essentially is an array of 2 arrays of 3 or 4, a 2-dimensional array of dimensions 3, 4. Okay. So that's what is the type of A. It's an array of 2 arrays of 3, 4. So that if you go, and then here you see inside the parentheses here, I'm going A plus 1. Now, A is an array. If I go plus 1, there's no such thing as plus operator between arrays, okay, or involving arrays. However, there's a plus operation on a pointer. So the compiler, what it's going to do is going to somehow, because there is what is called an operation which is called array decay to a pointer, which allows it to somehow translate an array into a pointer. So if you translate an array to a pointer, it basically returns the address of the first memory cell that is used to store this array. So that's what it's going to do. So when it computes A plus 1, so basically it decays A into a pointer, which is an address, and then adds 1 to this address. So basically it goes the first address that is used to store the array A plus 1 times the size of an element of A. That basically gives it the address of the second element of A. Now, what is A, as we say here? A is an array of 2, array of 3 and 4. So if you go A plus 1, what it does, it actually, A is this memory cell here, the address of this memory cell here, plus 1 time the size of an entire plane. So basically it goes this plus the size of an entire plane, which brings it here. So A plus 1 is actually the address of this memory cell here, okay? Because A itself is an array of 2 planes. So if you go A plus 1, it skips the first plane. So that's basically what is the meaning of A plus 1, okay? Now, for example, here is the execution of this program here. Now, if you print A, here I'm printing the value of A. There's no such thing as overloading the stream insertion operator for an array. So what the compiler does is basically it's going to say, oh, I can print an address. So I'm going to decay this A into an address. I'm going to print the address. Okay, so even decay is used here as you want to print A, which is an array which you cannot print. Okay, there's no such thing as stream insertion operator for an array. So it's going to print the address after having done decay on this array into a pointer. Then if you, so then that's why also for the same reason, if you print A plus 1, it is going to print the address of the first memory cell that contains the first element of the second plane. Okay. So in this case, A plus 1 is already an address, so it's printing the address. But of course, it needs to do the decay of A and then add 1 and then returns the address or computes the address. Now, so you can also dereference this pointer A plus 1 or this address A plus 1. That's what I mean here by address of the second plane of the array. Okay, so that's the address of the second plane of the array. Its type is address to a plane, essentially. So as it is, a type of this is address of something, you can actually dereference this address number and actually somehow get the thing that is being pointed to by this address, which actually is saying that star and then a parenthesis a+1 close parenthesis is this two-dimensional array that is the second plane of this three-dimensional array. However, if you try to print this, then it's trying to print an array. Again, it's going to decay this array and then print the address. Okay, so that's why it's printing an address here, right? Then the next thing I do is I add 2 to this array. So star a+1 is the array that is the second plane of my three-dimensional array. Then I do +2. So essentially, I'm doing somehow the same operation here. So I'm going to decay this array into a pointer. Then I'm going to add 2. So if I'm adding 2, then basically I'm going, I'm accessing the second element of this plane, which is the second or the third element of this plane, which is the third row inside of this second plane. Okay. So essentially here, this is an array. As you apply plus, then compiler is going to decay this array into a pointer, then add 2, which is 2 times the size of an element of this array, which is 4. Okay. Or 3, sorry. So then this is going to be basically an address, which is the address, sorry, which is the address. So we were here, and now I'm adding 2 to this, which is basically I'm going, I'm skipping 2 elements, and now I'm actually pointing here. So now I'm pointing to the last row in the last plane of this three-dimensional array. So that's where we at here. So now I actually dereference this pointer, which is basically saying that now I have a representation, the code that's resulting here is the type of it is an array of 4 integer. Okay. Then I actually apply +3 to this array of 4 integers. So it's basically going to decay this array of 4 integers into a pointer, apply +3, which is going to make me point here to the last element of this array, okay, of this array of 4 integers. And then eventually, I'm going to have the address of this last element here. And then, of course, if I want to have the value of this pointer to an integer or address of an integer, then I can use the reference on it. And then I'm going to access the value pointed to by this address or pointer. So let's see, basically, I'm going to print out the last value that is stored in this array, which is 24. Okay. So that's how decay is used here repeatedly when you evaluate this expression here. So first you apply +1 on A, which is an array. So it's going to decay this array into a pointer, apply +1, then you dereference, you get an array, you apply +2, you have to decay this array into a pointer, then apply +2, then you dereference, then you get an array, and then you apply +3 on this one-dimensional array. So you have to decay it and then apply +3, then you get a pointer to the last element. in which case you dereference it and yes, get the value at the end. Okay, so there's a whole cycle here of decay and dereference that is happening as you compute this thing here. Okay, and you see that it's actually inherently using this notion of offsets that is computed by the compiler. Okay, that was an example to show, what is this notion of an array being also a pointer. Some people say an array is also a pointer. When an array is not, when you store an array, it is not a pointer to the first element. It's not a pointer. It's just that you can decay this array into a pointer, which would return the address of the first element, first memory cell that stores the first element of this array. Okay, so that's it for that. So the next thing that we'll cover is the dynamically allocated array, which is going to be in the second video for this slide set. See you later.